Hi everyone, our group name is Sam's Club. I'm Brian Adams, and our project was airfoil optimization for firefighting aircraft. Wildfires were a mainstream issue during the start of the spring 2025 semester, and our team decided to take a closer look at the aircraft that fight these fires. The objective of this experiment was to measure the capabilities of the wings of these aircraft with the tools provided by Clarkson University. This was done using the following methods. First, we researched airfoils commonly used in the firefighting industry, and then we made 3D models for these airfoils with coordinate files. Then we used a wind tunnel and a force balance software that was installed called NIMAX to evaluate the lift and drag forces and acquire the L/D ratio. Performance was measured for 6 airfoils at frequencies of 2 and 5 Hertz in the wind tunnel at angles of 0 to 25 degrees in increments of 5 degrees. The key question asked in this experiment is which of the following airfoils used in firefighting missions has the best performance, and at what speed and angle of attack does it have these specs?
Hello, I'm Mark Heiser, and this is the method section. So our test plan for this was to find the various airfoils used by water bombing aircraft and then test them in the wind tunnel by 3D printing them and then putting them on the force balance to find the lift and drag, and then compare the efficiency of the different airfoils. Our experimental parameters, so we're measuring the lift and drag of the airfoil, and then we're controlling the airfoils, the angle of attack, and the airspeed that the wind tunnel is going. Our test equipment includes the student wind tunnel on the first floor of camp, a force balance with 2 strain gauges, one that measures the lift of the airfoil, and the other that measures the drag of the airfoil, and the interface board that connects the strain gauges to the computer, the NIMAX software to read the force data as a voltage in the computer, Excel to do math to find the lift and drag and analysis. And then we have 6 3D printed airfoils, each of which has an 8-inch span and 4-inch cord. We have 4 screws and 24 threaded inserts for the 4 per airfoil. And this is the calibration curve of the wind tunnel. This looks at the manometer height and converts it to an airspeed for the different frequencies that the wind tunnel runs at from 0 to 5 Hertz. And then we ran our experiment at 2 Hertz and 5 Hertz.
And next, we're looking at our procedure for the lab. So the setup is pretty simple. You take the 4 airfoils and we tap 6 airfoils. We tapped 4 holes into each of them, which align with the metal mounting software in the wind tunnel. Into those holes, we put the thread inserts mentioned earlier. And then once those are all set, we can screw an airfoil into the wind tunnel and run them at 2 Hertz and 5 Hertz between 0 and 25 degrees angle of attack, and record data each combination of speed and angle of attack, and then we repeat that for each airfoil. The budget for our project started at 0 and later turned to about $50. The wind tunnel and all software and equipment is free to use at Clarkson, and so is 3D printing for projects. Later on, we found we needed to use threaded inserts and screws that aren't provided by the university, and that totaled around $50. For our risk assessment, most align with running the wind tunnel, as if the airfoils are not secured down properly, they could fly out of the wind tunnel and create shrapnel and cause damage to the wind tunnel and people. We worked with Professor Hoover to find a safe way to mount them, and because of that, we reduced the risk greatly. And another form of risk is that the wind tunnel is very loud and could cause hearing loss. So we provided hearing protection that's at the wind tunnel. Here's our schedule. We were on time for each thing we needed to accomplish. There's a small break that we had for school breaks, but besides for that, we hit every goal we needed to at the on time.
Hello everybody, my name is Aiden Keefe and I'll begin over the results section. So for the first thing that we did was converting the millivolts to newtons, which we did this by the measured voltage and divided it by the calibration voltage, which is millivolts per newton, and this was about 1.47. First off, the first airfoil was the NACA 4417, which is the CL415 aircraft. And as you can see on the graph, the peak, the L over D, the lift to drag peaks at around 2.2, which is at 10 angle of attack. And then the NACA 23016, the Lockheed C130H, peaked at around 5 degrees angle of attack, and that was 2.65 for the lift over drag max. Then the NACA 23015, which was the Lockheed P3 air tanker, this peaked at 10 degrees angle of attack, and this was almost 3 L over D for the max. The NACA 4410.5 is the Lockheed 26 P2 Neptune. This also peaked at the 10 angle of attack, and then this was at peak about 2.65 for the lift over drag. And then NACA 4415, this is for the Air Tractor AT802F aircraft. This also peaked at the 10 degrees angle of attack, and this was around 2.65 for the max L over D. And then NACA 23017, the Conair Firecat, this also peaked at 10 degrees angle of attack, and this was about 2.214 for the max lift over drag. And then this just shows all the overall lift over drag ratios for all the airfoils. As you can see, the NACA 23015 had the best lift over drag max, which was at 10 degrees angle attack, where most of them peaked. There was, I think, 1 or 2 that peaked at 5, but most were at 10. And then these are the performance specs of all the different airfoils. They all have different root and tips of the wing. Then they are all turboprop engines. And then you have the power available, which is in horsepower, the empty weight and the max takeoff weight for each of the aircraft. And then lastly, we have the lift over drag max. So from there, we can use those numbers to find the range and endurance for all the aircrafts. Since they're all turboprop engines, they all use the same range and endurance equations. And they also use the same specific fuel consumption, which is C, and then also the efficiency, which is the NPR. And then the lift over drag max will change depending on what we calculated, and then also the weights. And then from here, we can see that the range was the highest for the P3 air tanker aircraft. And then the endurance, the Air Tractor AT802F and the P3 air tanker both came really close. Overall, the P3 air tanker did really well. And then we have the fuel burn rate, which basically just tells us how much it burns in a mission. So we have most of them are pretty low because the lift over drag is pretty low, and so I think it peaks at about 0.03 for the Lockheed 26 P2 Neptune. But then we also have the V-stall, which basically tells us when the aircraft will stall when looking at testing it. We have to calculate the CL max, which is the lift max over the density, the velocity, and the wingspan. And then we find that the V-stall was the highest for the P3 air tanker, which was 391 feet per second or 267 miles per hour. And then lastly, we have the uncertainty analysis. So we took the lift over drag max for each of them, and then we took the uncertainty of the drag and lift sensors, which they were about plus and minus 5%. And then we can see that none of them got over the 0.14 for all of them.
Hi, my name is Antoine Lacoste, and I will be doing the conclusion section. Key findings from testing. Among the 6 airfoils tested, the NACA 23015 emerged as the most aerodynamically efficient, achieving an LD ratio of 2.9896 with an uncertainty of 0.1456 at 10 degrees angle of attack. Its aerodynamic profile closely aligns with that of the Lockheed P-3 air tanker, reinforcing its real-world relevance in firefighting operations. The NACA 23015 led in nearly every performance category, including maximum range, fuel efficiency, and stall velocity, making it the best overall candidate for wildlife suppression missions. The CL415 achieved the lowest stall speed due to a high maximum lift coefficient, yet it underperformed in endurance and efficiency. The P-3 air taker offered the best range and strong fuel economy, highlighting a well-balanced aerodynamic design. These differences show how subtle geometric variations in airfoils can result in significant shifts in mission performance, especially under real-world conditions. For elemental challenges and uncertainty, testing was limited by small aspect ratios of the models, which naturally lowered the L/D ratios when compared to full-scale aircraft data. Force balance, calibration, wind tunnel geometry, and measurement resolution introduced small but notable sources of error. The Reynolds number achieved during testing were not representative of a full-scale firefighting aircraft, potentially influencing stall behavior and flow development.